Alright, so in this problem we're told that water is flowing through a multi-sectional pipe horizontally on the ground, and we know that the inlet velocity is 2.1 meters per second, the outlet velocity is 3 meters per second, and we can neglect the frictional losses. Now this diagram I drew is sort of arbitrary. The pipe might not be shaped like this in the transition region, where there is a sharp change in diameter. It could be different. I just drew it arbitrarily, and because we can neglect frictional losses, we know that whatever this transition region might be shouldn't contribute much at all to the pressure drop. Okay, so the first thing I think about in this problem is, can we utilize the Bernoulli equation, which states that, well, I'll just write it out here. P1 on gamma plus V1 squared on 2G plus Z1 equals P2 on gamma plus V2 squared on 2G plus Z2. Now this is true if we assume steady flow, streamline flow, an inviscid fluid, which essentially means friction is not a concern in the flow, and an incompressible fluid. With these four assumptions, we can utilize the Bernoulli equation. So since this pipe is horizontally placed on the ground, there's no height difference playing a role in the flow. So we can cross these out to 0. We're asked for the pressure difference between point 1 and point 2. Maybe I'll label that point 1, point 2. So since we know the velocities at both ends, and we can calculate the specific weight of water relatively easy, we can calculate the pressure difference. So I'll do some algebra over here. So if we rewrite this, I'm going to isolate P1 on gamma plus, that'll be minus P2 on gamma equals V2 squared on 2G minus V1 squared on 2G. Now if we multiply both sides by gamma, we get P1 minus P2, which is our pressure difference, is equal to gamma times V2 squared minus V1 squared on 2G. Since they have a common denominator, I went ahead and combined those. Now, it's also important to note that the specific weight is equal to the density times the gravitational constant. So when we multiply the specific weight throughout this term here, the gravitational constant will be canceled out, and only the density will remain. So P1 minus P2 then becomes the density, and I'll factor out this 2 in the bottom, times V2 squared minus V1 squared. So now we have an expression for our pressure difference. So let's calculate. The density of water is approximately 1,000 kilograms per cubic meter. Dividing that by 2. Multiplying this expression by our V2 squared, which would be our outlet, 3 meters per second. And our inlet velocity is 2.1 meters per second squared. And now P1 minus P2, use my calculator, 1,000 divided by 2 times the quantity 3 squared minus 2.1 squared. The calculator gives me 22.95, and if I check my units, I've got kilogram per meter cubed times meter squared per second squared, which is kilogram per meter second squared. Now we know we're supposed to get pressure, so I'm going to multiply this by meter divided by meter, which is equal to 1. And if I rewrite this, it'll be kilogram meter per second squared per meter squared. And this quantity in the numerator is a Newton. So this unit is the same thing as a Newton per square meter, which is the same thing as a Pascal. So our unit here is 2295 pascals. Thanks for watching. Please subscribe to the channel and continue learning more about awesome engineering. Have a great day.